All right. Hello, everyone out there. I'm Professor Charles Lindeman from Oakland University. I'm retired now, but I've spent most of my career teaching students their science. And I'm going to show you some things today that are things you probably would be able to do yourself. They're fairly simple, but they're kind of neat and fun, and I hope you will enjoy the show. We'll start with something everybody knows how to do. I'm sure you all learned how to juggle. That's in the third grade curriculum, right? So when I juggle, I throw the balls in the air, they fly, and I catch them. One can also bounce them, and now if I bounce this ball, hey, it didn't come back. Let me try this again. Whoa, something must be the matter with this ball, something wrong with it. Let me, if I hit it harder, nope, doesn't come back. You probably can tell what's the difference between these balls. These are made out of silicone rubber, and silicone rubber is springy. We say they're elastic. This one is a beanbag, and it's soft, and it's filled with little nutshell fragments. And when this one hits the ground, it doesn't come back. Now, why is that? Well, this one has the ability to change its shape, and the little beads inside rub against each other, and that can essentially use up the energy that I put into the ball. And when they rub against each other, like rubbing your hands against each other, the energy is converted to heat. All right? So if you try that with your hands, you rub them together, you'll feel that they warm up. So energy that we put into something, in this case, the movement of the ball, kinetic energy, can get converted into heat if friction is involved. All right. Materials that can store up the energy and give it back, like the ball, we say those are elastic materials. Another elastic material I'm sure you're all familiar with is a balloon. All right. If I blow this balloon up, I have to force air into the balloon, and that makes it stretch. But the stretchiness can make the balloon spring back to shape and force the air back out again, and makes the balloon fly around. That, by the way, is the same principle that makes it possible for scientists and engineers to build rockets. All right, the flow of the air coming back out of the balloon develops a push, a thrust, and the balloon flies around. So the energy I put in to blow that balloon up was given back again when the balloon sprang back to its original shape. You're mostly familiar with rubber bands. I know a lot of students are familiar with this trick with rubber bands. You pull a rubber band, you store energy in the rubber band. When you let it go, the energy comes back and the rubber band goes flying. All right. Elastic materials have that property, that when you store energy by pulling on them, oh, there it is, here's my little rubber band. When you store energy in them by pulling, they give it back when they are restored to their original shape by their elasticity. Another principle that we're all familiar with is gravity. Okay, when you objects are let go, we know they fall to the ground. You fall to the ground if you trip. This is an interesting little sidelight, is that if I do this to the balloon, now it doesn't fall to the ground. It's staying up there on its own accord. Can you figure out why? That it's not, is gravity not working all of a sudden? We have a problem here. Gravity seems not to be doing its job. But another force of nature is doing its job there, a force that we call static electricity, and it seems to be able to overcome gravity. Now I have here a comb that was given to me in Lothlorien by Galadriel. Scientists travel a lot, you know, and I traveled to Lothlorien, and Galadriel was kind enough to give me this magical comb. You can comb your hair with it, but you can also use it to pick up objects. Now, I don't know, you might have a comb. You could try it yourself, you see, and see if your comb is magical. See if your comb can pick up objects. These, by the way, are called peanuts, but those of you with peanut allergies don't have to worry. These are the kind of peanuts that are used to pack material in boxes for Amazon and other sources of material. Now, this comb has another magical property that is really kind of cool. Here I have a device that's very sophisticated that I built myself, and it's got in it a valve. You might recognize this valve at the top. If I turn the valve, it turns on the flow of water. All right. If I use my magical comb now, comb my hair with it, I can make the flow of water, and I can even move it so that the magical comb pulls the water outside the cup entirely. So you don't have to take my word for it. You probably have a comb of your own, and you have a bottle of your own. You can see if you can make a magic bottle with a magic valve, and see if you can also bend the flow of water with your magic comb. Now, this is a common object that you probably have in your cupboard. I swiped one from my wife's cupboard, and I spent many hours teaching this to drink. It's a bendy straw. You put it in the water, and well, if you're good, which I'm not apparently, if you're good, you can teach it to drink from the cup on its own. Now I got to tell you that bendy straws are kind of stupid, and it took me a very long time to train this comb, this straw. So don't be discouraged if your straw refuses to drink the first time you try it. But I would encourage you to try this experiment yourself, and also to figure out for yourself why the straw can drink out of the cup. It's a very interesting physical principle that makes it possible, and it has to do with pressures and flows and the weight of the water. All right. Now, speaking of water and pressures and flows, I have another little interesting thing to show you. That this is an ordinary piece of paper that I just cut out. This is an ordinary jar. All right. If I take my jar and I fill it up with ordinary water from an ordinary tap, and I put the piece of paper over the top carefully and turn it upside down carefully, you'll notice that it's not losing the water. Just ordinary paper, no big deal. Ordinary peanut butter jar. Can you figure out why the upside down jar doesn't lose the water? Isn't that rather amazing? It's actually also due to understanding pressures and flows and understanding that the water can't come out unless air can get in. Okay. If I do the experiment over again, and this time I touch the paper, all right, and let air get in, all of a sudden the expected thing happens and it falls out of the jar. Now the next thing I'm going to show you is a little bit different. It's a different experiment altogether, but it's also very curious, and it illustrates another principle of nature. And that principle of nature is magnetism. You probably all have seen magnets. You know a little bit about magnetism. All right. This is just a weight here to keep the board from doing anything crazy. I built here a magic wand. Okay. You'll see the little magnet that's on there. It's called a neodymium magnet. You can get one at Michael's. They sell them also in some hardware stores and department stores. Neodymium magnets are very strong magnets. They're really cool. If you do get one of these to play with, they come on a card. Be careful you don't let little brothers or sisters play with them, because if they get swallowed, they can be very dangerous to little children. So I know you're old enough to understand how to play with magnets, but if you notice now, if I let this magnet hang, all right, it only wants to point in one direction. It becomes a compass. It's telling me that that way is north, all right? That way is south. An amazing thing I just learned myself not that long ago is the North Pole of the Earth is the magnetic South Pole. Can you believe it? The North Pole of this magnet points towards the North Pole of the Earth because the Earth's magnetic pole is a South Pole. Don't tell anybody. Now this magic wand, I glued the magnet onto the end of a little stick. If I use my magic wand and put it near the neodymium magnet there, the other magnet seems to worship it, and it does something called magnetic levitation. Fancy word. Boing, plunk your magic twanger. And as you see, the other magnet is scared and it jumps up. These are made with pieces of cardboard and little pieces of cloth that I took from my wife's knitting collection. And these are neodymium magnets. So this is something anybody could really make. You just need a little bit of spare cloth. And you need some patience, because these strong magnets, they really pull each other. Ah! Boing! All right. That's called magnetic levitation, okay? The next thing I'm going to show you is a classic experiment. A classic experiment that was done by Galileo Galilei. Galileo Galilei, famous scientist. Galileo Galilei was sitting in church one day, and he wasn't very interested in the church service. Some of you probably have had that problem yourselves, I would guess. And he was watching the chandelier in the church, and he noticed that the chandelier was swinging back and forth. Right? The breeze was making the chandelier swing back and forth. And he timed how many times the chandelier went back and forth using his pulse, right, as a timer. And he found that the chandelier always swung back and forth the same number of times, no matter if it was swinging with a big swing like that, or if it was swinging just with a little swing like that. And he decided to go back to his laboratory and test out whether that was really true. And he did the following experiment. Right? He made pendulums, and then he made them with different kinds of material as the weights, as the bobbers on the pendulum. And he found that if the pendulums had arm strings of equal length, they went back and forth together with the same period. It's called the time a pendulum takes to swing back and forth is the period. Right? And if he changed the length of the string, the period became faster, and they no longer stayed together. So the length of the string of a pendulum determines the period and the frequency, how frequently it goes back and forth. If you can get the lengths exactly the same, they will swing back and forth with just the same period. All right. From that, he decided that this would be a perfect way to keep time. And he proposed that you could build clocks using the swinging of a pendulum as the mechanism to keep the clock moving at a uniform period of time. And it was the basis for the pendulum clock. And it was the first way of taking accurate measurements of the passing of time. And it's very important when you're doing scientific experiments to be able to measure time accurately. This is an experiment that took a piece of wood, string, a couple of marbles, all right, and it demonstrates a very, very famous experiment in physics that led to the development of accurate timekeeping pieces, clocks. Now, this kind of pendulum you could make a very nice science project out of and explain to people why it's important and why it works. A different kind of pendulum I designed, and my pendulum, because I'm a little bit of a science nerd, my pendulum works a little differently. It doesn't like to swing back and forth. It likes to go around in circles and bounce. It's sort of a crazy pendulum, and the crazy pendulum is a trick that I devised. All right. All right. Can you guess why my crazy pendulum does not like to hang straight down? My crazy pendulum seems to avoid hanging straight down at all costs. All right. Well, I'll give the secret away. All right. All it takes is to mount a magnet in the board on the other side and then cover it with a piece of tape, so you can't see the magnet here, but it's there. And I made it so that the pendulum has the same pole facing down as the bottom magnet has facing up, and like poles of magnets repel each other. The last kind of pendulum I'm going to show you was devised not by me, but by Isaac Newton. And it's a really cool type of pendulum. As you can see, it has multiple balls hanging on threads. and they're lined up so that the threads keep them centered all in a nice straight row. This is hard to build on your own, and I cheated. My wife bought this for me at a store that sold novelty devices, a craft store. But you could build it. This is fishing cord, and these are just this is just a metal frame. But you can also buy them. You can buy them off the internet. It's called a Newton's pendulum. And the thing about Newton's pendulum is it demonstrates a principle of nature called conservation of momentum. Just like my springy silicone juggling balls, these steel balls are actually very elastic. When they hit each other, they deform and spring back to their original shape. Although you can't see it, it's a highly elastic material, and the collisions are highly elastic. So they transfer their energy to the next ball in line until it goes across to finally to the last ball in line. And in order to conserve both the energy and what's called the momentum, right, if you pull one ball, you get exactly one ball to move off the other side. If you pull two, you get two to go off the other side. And one ball stays relatively stationary in the middle. If you do something really crazy, like the two balls on each side transfer their momentum to the two on the other side, and the middle ball just acts as an elastic buffer that allows the energy and momentum to pass through. I find that very cool. I really like that. And you can play with one of these for hours. I'm a little kid when it comes to playing with things like this. And here, you can make 3 and 3 come flying off. Newton's pendulum and the principle of conservation of energy and momentum in an elastic collision. Very much fun. As I said before, all of these things are designed so, you could actually make them. This is a dowel you can get at a hardware store. This is a piece of wood that I got out of a box that was part of a packing material. These are nothing fancy. These neodymium magnets are available at craft shops. These styrofoam peanuts I saved from a box that had packing material. Rubber. These are sold at any party store. Balloons, rubber bands. I'm sure you've got those. Pieces of paper, a peanut butter jar, plastic cup, empty pop bottle. All right, with a magic switch to turn the water flow on and off. Comes right with the bottle as part of the deal when you buy the pop. All you need to do is remember to save it and take the label off, and you've got it. And of course the straw, quite stupid, but can be taught to drink, and a very, very handy little device to demonstrate the siphoning principle that is based on pressure and flow. I hope you enjoyed the little presentation. And I hope you try some of these little tricks yourself. They actually do work. There's no hidden, well, except maybe Galadriel's comb is special. But the rest is stuff that you can prove to yourself that it works and amaze your friends. Hope you had as much fun as I did, because I enjoy this stuff. It's a lot of fun. See ya.